Thank you very much, Michael. It's a great pleasure to be here, and I thank my colleague Barbara for steering me this way. And it's, as Michael says, I think it's very, very important in an interdisciplinary sense to connect the people in the computer science, applied math, of course, the design people for the big machines and such, and then, very importantly, the application domains, because this is where all of this comes together and has an impact on what we do in our daily lives. And the various governments of the world have made this a very strong motivational sort of thing. It's not just in the US. I'll speak to that in a minute. And so, as Michael mentioned, my background is in astrophysical sciences. The practical application domain that I'm focused on is delivering bountiful clean energy associated with the fusion energy reaction. And the connection between astrophysics and this is that the medium that we work in deals with a very hot gas of charged particles called plasmas. And the connection back to astrophysics is that over 99% of the visible universe is made up of plasmas. So by way of introduction, the focus of my presentation today is on HPC performance scalability and also portability, because there are lots of different high-performance computing architectures being developed. And so if you have a very useful application, you really want to be able to port it and be able to deliver good performance on a variety of different architectures. So I'll talk about aspects of that in a representative application domain. This is not meant to be a focused fusion energy type talk. I'll give some introductory comments about it, but it's more illustrative that the more advanced, sophisticated type computer science technology that's being applied to the application, like OpenMP, that this is that if you identify an application domain like fusion, then you can see what the pipeline is, so to speak, in terms of what this leads to. So fusion energy science there's a reference here. The slides are left behind. People can look this up if you'd like to see it. This is a publication that came out in SCIENCE, the Computing in Science and Engineering publication, just this past year. The current progress that we're going to talk about here is the deployment of innovative algorithms, including OpenMP, with a modern code that delivers new scientific insights on world-class systems. This speaks to the portability issue. And we've worked hard over the course of the last couple of years to deploy this discovery science-capable code on these top 7 supercomputers in the world. And in the near future, we also have an entry to the largest projects in the US, such as Summit, the 100 petaflop system at Oak Ridge National Lab. We're also part of Cori, that Helen will talk about later, and also on the NSF machines and such too. So I'll make some comments on future progress, what the needs are, and emphasize throughout that it's not possible to achieve significant progress in a timely way without a true interdisciplinary sort of research environment to carry that out in. Very clearly, one cannot flip products over the fence and expect things to happen. So this is a slide that I borrowed from Jack Dongara from a talk that he gave at the beginning of this year before updating this to the 2015 machines. The main, you've probably seen all this, is the top 500 business, and this is where our iPhones and laptops and things are going. The progress is really dramatic, and so, and it doesn't seem to be stopping, as you've heard throughout the conference. So what does this mean? Well, as we've said earlier, you want to speak, what I want to highlight is the imperative for applications impact, the actual value of extreme scale HPC to scientific domain applications and to industry. And the context, in some respects, is in the US, there's a major initiative called the National Strategic Computing Initiative. The White House has energized the across the board pretty much the OSTP and OMB, the main agencies that sit above the Department of Energy, NSF and so forth, to mobilize major activity that will accelerate the pace to exascale and beyond. But also in the announcement they said that it's very, very important to see the direct benefits, accelerated progress in things that the U.S. cares about. And things are quite exciting right now and are moving forward pretty rapidly already. So what are the practical considerations as you think about this? You need to get better buy-in from science and industry. What does this require? It means moving beyond voracious, more of the same, just bigger and faster type computations to what we call transformational type advances, which means the achievement of major new levels of scientific understanding in a particular application area. This involves improving the observational, experimental validation, and verification, verification is purely theoretical or computational, but this involves, for example, cross-verifying against analytic type estimates, also cross-code comparisons using different methodologies and such. But the real-world test is to compare against the observational information, to enhance the realistic predictive capability. And this is interesting that these days there's, in addition to the hypothesis-driven so-called first principles type approaches that we typically apply HPC to, the huge area of growth is in big data-driven statistical approaches, machine learning, and the like. And I think very quickly we're going to see a complementarity between the two. We need to deliver software engineering tools to improve time to solution and energy to solution. What do I mean by that? The major sort of hero calculations that you carry out in any application domain, to the application scientists, the coin of the realm is what? Is how long does it take? But in addition these days, because the computers also chew up a lot of energy in carrying out big calculations, what is the energy to solution? So these metrics of time to solution together with energy to solution, very important, and I'll illustrate that a bit in what we're talking about. My colleague David Keyes at a conference this past, just a couple of months ago at Argonne, I thought a quote from his presentation was very relevant to today. Billions of dollars of scientific software worldwide hangs in the balance until better algorithms arrive to span the architecture applications gap, and this is very true around the world. The associated challenges you're aware of: hardware complexity, heterogeneous multi-core involving GPUs with CPUs. Good example is Summit, the 100 petaflop project in the US. It's that is at Oak Ridge National Lab, and then the MIC and CPUs, which will be in the 100 petaflop Aurora system at Argonne National Lab. The software challenges involve, at the most fundamental level, it's very hard to pull people away from their legacy code approaches because so much has been invested. The legacy codes are still going to be useful because you need it for what? You need it for the verification aspects of things. Before jumping to your new engine and such, you have to verify that it does what you want it to do. The software challenges, though, do force you to consider significant code rewrite, and we've done that in our particular applications. The imperative here is, what is the level of accountability? Everybody can just say, well, all right, all this new technology, we want to be part of it, we need it. But how have you demonstrated that you deserve to be funded to get the resources? So you need to provide specific examples of impactful scientific and mission advances enabled by progress from what? We don't have collective Alzheimer's, so from the terascale to the petascale to today's multi-petascale HPC capabilities. If you want to apply for resources of this kind, you should be able to demonstrate what have you done before, what have you delivered, what were the transformational changes. So this is just a bit of an intro to the application domain. CNN has done a series called Moonshots for the 21st Century, hosted by Fareed Zakaria, and there are 5 segments broadcast very recently, spring of 2015, on CNN with all their production values and such, and it's very accessible. These are not very long presentations. Each of these grand challenges for the 21st century, including fusion energy that I'll talk about here, includes mission to Mars, human heart, hypersonic aviation, the human brain. And it's a very, very good series, and it's very, very accessible introduction to these grand challenge areas for the 21st century. So, so what about fusion? What is this? The most widely subscribed to approach involves confining this very hot plasma that I talked about, this very hot thermonuclear gas, with magnetic traps, because you cannot keep it confined unless you use the electromagnetic fields that work on the charged particles. Remember I said that these are all charged particles in the system. And so this is a donut-shaped machine. It's called a tokamak. The Russians invented it first a long time ago. And this is the basic fusion process where you take the isotopes of water, basically deuterium and tritium, and you subject it to a lot of heat. The fusion reaction occurs under the proper condition, and if you're successful in doing that, then the constitutive products, an alpha particle and a fast neutron, come out, and there's less mass here than here, and according to Einstein, that gets converted into energy. The energy multiplication factor is about 450 to 1. This is the reaction right here. So you're confining in an extremely hot plasma, several hundred million degrees, confined by a strong magnetic field. So this is like the surface of the sun, these sorts of temperatures greater than that. But there's various things. In physics language, the thermodynamics always will try to drive the particles and the energy out of the confinement region. The Mother Nature wants everything to be uniform and flat. And one of the ways that it achieves this is through turbulent processes, very rapid transfers, physics mechanisms for energy leakage from the magnetic confinement system. And this is what we combat in this application domain to try to make this fusion reaction happen. And if you do, as I said, the energy multiplication is huge. So this is a list of all of the very attractive aspects of fusion energy. That CNN report talks about aspects of this. It's abundant. Comes from water, comes from the oceans. Deuterium and tritium are very easy to find. A fusion reactor cannot blow up or melt down, so it cannot. There's no risk of nuclear materials proliferation. Lots of ideal sorts of aspects. And some people joke about fusion and say it's the energy source of the future, and it will always be the energy source of the future because it's very, very hard to harness. And so we don't make the pitch that this is the only thing you should concentrate on. It's quite complementary to other attractive energy sources as long as they're safe. For example, the natural sources, wind and solar and so forth, are great, but they're not going to supply in a carbon-free environment, freedom from fossil fuels, enough energy for you to be able to move forward. So this is a nice plot that I like to show because to counter a little bit the comment that fusion is the energy source of the future and always will be, there has been a lot of progress. Beginning in around 1975 when I was just getting out of grad school and such, until the mid-90s or so, what's shown here is the energy production out of a fusion confinement device like a tokamak over the years. And here there's a very rapid rise. American flag denotes the machine that was at Princeton University at the, Michael mentioned where I'm at the Princeton Plasma Physics Lab. And what was achieved here is if you measure how much energy comes out versus how much energy goes into the reaction, here it was about 2 parts in 20,000. Here it's about 0.2. So you went up a huge factor in 20 years. And this is if you plot it against the famous Moore's Law empirical curve. This is steeper than the Moore's Law curve. But unlike new laptops, as I showed in the other slide, quite frequently you're not putting a new energy source out. The delivery period is a long one. And within 3 years after the US made this achievement of getting out, this 0.2 ratio of energy out versus energy in, the Europeans, the EU, came up with a more powerful machine that's still operating that set the world record of 16 megawatts of fusion energy delivered. And here you reached almost break even, which is energy out is almost equal to energy in. It's about 0.8. And this motivated the targeting this huge project called ITER, because you now have to keep the confinement sustained for a long period of time, and you have to use superconducting materials and such, so it's expensive. And this is a $25 billion project that's being constructed in the south of France. That CNN clip also shows the construction, and this is the grand challenge to deliver this. This involves the engagement of 7 governments representing over half the world's population, and it would demonstrate the scientific and technical feasibility of fusion power. So it's going from the 10 megawatts or so that can be confined for about a second with a gain of order unity today, to going to 500 megawatts for greater than 400 seconds with a gain greater than 10. So when people ask me, have you achieved this, what does this mean in terms of delivery of fusion energy? This would be if you hit a gain of between 10 and 20 in this ITER device, that you'll be about where the Wright brothers were at Kitty Hawk. The plane will fly, okay? But if you had interviewed the Wright brothers, then they would not have been able to tell you it's competitive with trains and boats as a form of transportation. So you would need a lot of technology and such to drive it forward. But I would submit to you that energy futures are more important than transportation. The governments around the world, for energy security, lots of reasons, will really go aggressively into this. This is a huge consortium right now, as I said. The main participants are the EU, that's why it's based in France, but the US, China, Korea, Russia, there are many partner nations are involved in this. So I'm not going to dwell on this. These are the basic fundamental equations. This governs the distribution of particles in the system. This, in a particle pushing sense, these are ODEs, these are force equals mass times acceleration type things. This is the way that the distribution function is represented. And then if you just did this type of simulation of the confined hot charged particles plasma behavior, it's very much like a Monte Carlo type simulation, and everyone understands what a Monte Carlo code does. But the additional challenge for plasma physics type calculations is that you have to self-consistently solve for the field, and these involve solving Poisson-like equations, linear PDEs and Eulerian coordinates, or the so-called lab frame, and there are 3 of these equations that you have to solve, coupled to solving self-consistently for the distribution function. So these give the forces that push the particles through the system. And this is like an exaggerated schematic of this donut-shaped magnetic confinement system. This shows the radial cross-section. The mathematics involve a 5D so-called gyrokinetic Vlasov-Poisson system. The numerical approach is well established. Particle and cell methods are very well known. And gyrokinetic just means that as physicists, we look at the problem and just say, you don't have to do it on all time scales. If you do a fast averaging, then you pick up the essential behavior that you need. And so that's why we call it gyrokinetic. You average over the very fast time scales to get at the key dynamical processes that you're interested in. So so here, basically, it shows that in the past decade or so, you moved up from This is a typical sort of simulation. 130 million grid points, 30 billion particles over 10,000 time steps. These are not individual particles. These are like supersized particles. Otherwise, it's impossible to push like Avogadro's number of particles. But electromagnetically, the sound foundations are very well established that you can push these supersized particles. So the objective is to develop an efficient numerical tool to realistically simulate turbulence and associated transport in these magnetic traps using high-end supercomputers. And this is, again, another cartoon schematic. You just distribute the particles on a grid, and the charged particles will sample a distribution function. The interactions occur on this grid with the forces, as I mentioned, determined by the gradient of the electrostatic potential, which is calculated from the deposited charges. The grid resolution is dictated by this electromagnetic quantity, the Debye length, that leads to finite-sized particles up to this gyro radius scale. And so these are the fundamental particle and cell operations involving the gather-scatter sort of process. And I won't read through all of this. I don't want to run out of time here. So you basically repeat this process over and over, and you can associate this with identifiable, well-identified functions that for optimization purposes, it really focuses you on what you need to do in terms of the operations. And so this just basically repeats what I just said in more detail. The particle and cell approach involves two different data structures and two types of operations. Charge, particle to grid interpolation, this is the scatter process. The Poisson or field solve, this determines the forces on the particles as you move time evolve it. And then you push it, the grid to particle interpolation. This is the gather process. So getting down to what this impacts, this is a plot of, this is like, how well do you keep this hot gas confined? This is a measure of the confinement characteristic. This determines the size of the machine, because what we in Princeton tried to do was to address this, the very fundamental problem of if you go from a small system to a large system, it's a fundamental problem size issue. But there's no free lunch as you go from this is like a very small device. This is like the size of the devices in the US and in most of the world. This is the joint European torus, so this is going out in size, as you see. And then you hit ITER, the $25 billion machine being constructed now in France, and the machine size is getting bigger and bigger, and there's no free lunch. You know, you have to provide the spatial and the phase space resolution to be able to resolve the problem well. About a little more than a decade ago, we delivered multi-teraflop simulations using 3D particle and cell codes, and this involves the quantities that I just mentioned to you. And you push this forward over 7,000 or so time steps, and we're able to do a very rough estimate of what the confinement is like as you go to ITER. And this is the trend that it's a predictive trend, so this is scientific discovery. If you just look at things empirically, it's mostly here, and the trend is pretty steep, but then it does roll over. The physics tells you that it will roll over, but you need more physics understanding to really trust this result. And so to do that, the excellent scalability of the PIC codes on modern platforms will enable the resolution and physics fidelity that you need for the physics understanding for a large system. But efficient usage of the current leadership class facilities worldwide demands, as I mentioned earlier, code rewrites featuring modern computer science applied math methods, including OpenMP, to address the extreme concurrency, data locality, and memory demands. So in our own work, at Princeton, we were greatly aided by the US Insight projects, which provided lots of cycles on the leadership class systems. We also participated in the international G8 project. There was 6 topics, 6 problem areas were selected, with one being fusion. I was the US PI for this project, and the interesting aspect of this in terms of portability is that we were given access to the top supercomputers in that consortium. So we were able to run on the big machines in Germany here, in Jülich Supercomputing Center, on Japan's #1 machine, the K computer in Kobe. So that was a very stimulating test bed to do things. So let me get to more specifically to the role of OpenMP in addressing these challenges. The extreme concurrency adopting OpenMP is one of the most efficient algorithmic approaches to facilitate efficient multi-threading, which you need to engage all these tremendous numbers of processors. I mentioned portability. Except for GPU hardware, which requires a bit more work, OpenMP works with all multi-core processors. Ease of deployment is that it's now a very mature implementation, relatively easy to use. The easiest approach is to deploy OpenMP at the loop level. OpenMP worked best at this level in the late 90s and early 2000s when it was introduced, and has remained the best approach in most all application domains since then for dealing with multi-threading and challenges of this type. The example in our application domain, these are all global particle and cell codes. The most prominent global fusion energy particle and cell codes all use this methodology. In dealing with making incremental changes, you can implement OpenMP parallelism in an incremental way, one section at a time, without affecting the rest of the code. So it's a very important feature if you're trying to bring along legacy codes to be able to handle this, large legacy codes. The intranode parallelism, OpenMP is ideal for intranode shared memory parallelism, we found. So OpenMP is not meant to replace MPI, but very hierarchical. Hardware requires hierarchical solutions. So while MPI is still the de facto solution for internode communications, many currently would argue that a PGAS language works better in some cases. There's also, in addition to, remember I mentioned that in addition to pushing the particles in a Monte Carlo-like scheme, you have to self-consistently solve for the fields. And this involves these Poisson solves. And as you try to deploy your modern code on modern supercomputing platforms, it's very important that the solver technology comes along for the ride. And the main solver packages, the main issue that some of us have with it is that they're not quite ready for dealing with the OpenMP needs for being able to deal with multi-threading and such in the solvers. Examples include major code packages in the US like Argonne National Labs PETSI code, which is a big solver package that most of you are probably familiar with, or Trilinos at Sandia. But in more recent discussions, we believe that Lawrence Livermore Labs hypercode is very suitable, especially for portability purposes and such. So the challenge is to incorporate multi-grid Poisson solves with OpenMP to efficiently deal with extreme concurrency, multi-threading issues, characteristics of near future systems coming up. Also, the enhanced physics that we bring to the table, you have to move beyond just the simple electrostatic field solves to fully electromagnetic solves. So while you may not be investing a tremendous amount of compute time right now on just the solver part, you soon will need to as you move to the next physics stage. So, and what we're promising in terms of physics deliverables for Summit and Aurora says you really got to get moving on the solvers, and you better make them OpenMP compatible. And so we're aggressively moving forward on this right now. We're involved in the early science application program at Oak Ridge that leads to the Summit system. And so our particular project, we're one of the 2 fusion projects that were selected out of about a dozen for the early science for Summit. And this involves a partnership between our project in Princeton using this gyrokinetic toroidal code Princeton, together with our what we call our flagship large, more legacy-oriented code that is still a very, very scalable particle and cell code that is centered at UC Irvine right now. Actually, this was developed at Princeton. Professor Zihong Lin, a number of years ago, he was my student, and he's done very well. He's a full professor in physics at UC Irvine, and he's also the lead in China for an ITER China simulation program. So we've teamed up for this early science project at Oak Ridge, and one thing is very clear: we'll require that the requirements for a multi-grid electromagnetic field solve with OpenMP, such as Hyper, is something that we will definitely aggressively pursue. Other things, radial domain decomposition. I'm not going to read through all of this, but OpenMP provides the best way to address this grid-based issue. And what this involves is, remember, what we're trying to focus on is to efficiently calculate increasing problem size. And domain decomposition means a way of more efficiently representing the algorithm such that the memory footprint is reduced as you go to larger and larger size. And the way to make it happen is, we found, you have to use OpenMP. Provides the best way to address associated grid-based issues. I wrote this on the slide so people can read this. I'm not going to read this to you right now. I'll never get through the talk. The other important area where OpenMP is very important is in heterogeneous acceleration, the GPUs and such. While offloading particle-based subroutines for acceleration on GPUs or on Xeon Phis for acceleration purposes, usually a single MPI is launched on the host or CPU for grid-based work. OpenMP enables multi-threading capability more readily to avoid performance degradation of the host as we shift towards multi and many cores on today's architectures. This you're probably quite aware of and puts a greater emphasis on the utility of OpenMP. And as other talks have emphasized during the last day or so, OpenMP is not going away. It's really very, very usable, and it doesn't mean that you hit a ceiling in terms of improving, but it's certainly something that will be featured in the application domains as we go forward. This graph is an illustration of our code in Princeton GTC. It's portability. This shows how much of the top 7 supercomputers around the world to what level they've been engaged. And this is the Blue Gene Q system at the Lawrence Livermore Lab. We were given access to that, and we ran the thing at full scale, of course, on Mira. This is Blue Gene Q. K-Computer through the G8 project. We basically replicated all the performance scaling properties, just going up to about 40% of the machine. And then the others are here, including Stampede and Tianhe 2. These are the big Xeon Phi systems, and as I note here, the progress that we've made on this has been hampered by the fact that both of these, the experts at these facilities have said, if you use a symmetric approach, symmetric algorithmic approach, and I'll talk more about that in a little bit, you scale just fine, just with a C language program, up to about 1,000 processors. But beyond that, you have to go into the so-called offload mode, where the communications challenges are really tough and the efficiency becomes much more difficult. And so we haven't been able, so we went up to about 50% of the capability of the #1 machine, Tianhe 2, but this is all CPUs, okay? And I'll talk a bit more about that. And the dark hatches indicate how many used nodes and how many unused nodes there are. And this is just a quick reminder. I showed you that other result as you go to larger and larger machines, the confinement degradation. This is tackling a different type of physics instability process that is more difficult because you're tracking the electron dynamics, which move faster. So the use of accelerators and things is really important. But to cut to the chase, these are new results that we achieved in the last 3 months or so, and we can replicate this trend and replicate this plateauing as you go to larger and larger size systems. And these are real hero-sized calculations because you really had to use the full power of the modern supercomputers to achieve these results. And so getting back to the code properties, there are 6 major subroutines in a global particle and cell codes, and these are listed here. Again, we talk about the gather scatter, and this is something that's very important in our interactions with the performance modeling community in this area, because when they look at the properties of new architectures that are coming up, it's very hard to focus down on a few functions and things. For this class of particle and cell codes, there's only half dozen or so here. And so when I talked to Torsten Hoffler, who's the head of the Intel Center of Excellence in Zurich, he says this is great. And so we're working with him right now and being able to look at the future architectures, but focusing on a limited number of operations. And this really facilitates progress. And so the idea is if you do performance modeling on a particular architecture, and you can translate that to a smaller number of operations like this, then you can very quickly jump into the actual real application code. And so the people involved in performance modeling are very interested in this type of approach. This I'm not going to dwell on. This shows the weak scaling results on various supercomputers, Titan, Blue Waters, Mira, et cetera, and these, what are these things? These are the particle and cell operations that I talked about. And this is the breakdown of performance in terms of just how much time these different operations use. A cleaner version is this, just focusing on a few here. This shows CPU-only performance. This is the wall clock time per ion time. Ions are, the larger charged particle in a fusion plasma. Operations on Mira, Titan, and P-Stant. This is the #1 supercomputer in Europe right now at the Swiss Supercomputing Center. And then this shows the performance on Titan and P-Stant on a CPU plus GPU. The operational breakdown of time per step when using 80 million grid points, 8 billion ions, 8 billion electrons, and 4,000 nodes on these systems, and shows the relative performance. And the interesting thing is if you plot it this way, what this shows is that here again is the wall clock time. This again are the A, B, C, D. This is as you go to larger and larger problem size. These are the number of nodes engaged. The number of particles per cell is 100 particles per cell. Typically, when I showed you the other calculations, the particles per cell is chosen to be around 10 or so. So we're at least we can actually go up to 1,000 if we need to. So this indicates that for this code, the GPU acceleration gives you a speed up about a factor of 2. But interestingly, if you look at the scaling, this is performance scaling, and we're using the same code for all cases, although we've written the code in C language and in CUDA. And the interesting thing here is CPU only on Titan. And this is not good. You want things to be as flat as possible as you go to larger problem size in terms of wall clock time spent doing the calculation. So this is a P-Stant, CPU only, but the outstanding aspect of this is that it deploys the Aries network. Okay, so the communications are much superior to what is on Titan and Blue Waters, and you can see a significant difference in terms of wall clock time for execution. If you then look at the hybrid performance, CPU plus GPU, you see the wall clock time has dropped, and this is for Titan, but it still keeps on going up like this. This is much flatter for P-stant. And this is all due to the Aries network, we believe. The performance difference is very reproducible this way. And it emphasizes that for particle and cell codes, that this, the network is important. And it speaks to, now if you talk about co-design activities on the Summit project, now you have different partners, right? And now you have IBM together with NVIDIA. They've done a major switch here. And who's providing the communications? Aries was developed by Cray and deployed successfully on P-stant. It's not on any other machine in the US. It does make a significant difference. So is Mellanox going to step up to the plate and give you the communications that you need? Are you going to really be able to ramp up the communications capability commensurate with this 100 petaflop project? We don't know, but that's a major challenge. So this shows, I've been showing you weak scaling, which is more indicative of what happens as you increase the problem size. This is strong scaling, which basically says if you, for a fixed problem size, a big one, you can really carry out more and more intensive studies. And we've done this with the full electron dynamics and looked at 80 million grid points, 8 billion ions, and this is the full big production run codes. This is plotted on a log-log plot, and it shows this. So what's the takeaway from this? Blue is the CPU large IBM Blue Gene Q system. Titan is the hybrid GPU-CPU system, and this is P-stant. And again, this is wall clock time, so lower is better. And here's Mira, and it does, very, very well. As you go to up to 32,000, 33,000 processors. Titan doesn't do so well. It's faster because of the GPUs, but here, as you go to many, many more nodes, the communications make a difference, and you see it roll over like this. But P-stant is very steady. It's not as a large system as either Mira or Titan, but for the plots that we're showing here, it does very, very well up to over 4,000 nodes. So this is an important lesson learned from this. This is a more dense plot, but it shows our full effort that was achieved a few months ago. We weren't able to do very much with respect to Tianhe-2, CPU only, but you can see that's the plot here. Wall clock time, it's the fastest because you can really employ, it's a very powerful machine. But again, P-stant holds its own very well up to 4,000 or so processors. And going beyond this, even for P-stant, you really had to go to the offload mode. And we're not ready for that, or we haven't developed enough efficiency. And some of the things that we need to discuss in some of the comments with people after their presentations yesterday, we really would like to get more insights into how to improve performance on the Xeon Phi systems, and Knight's Landing in particular. Knight's Landing for going into the future, but Knight's Corner as it exists right now. Dungar and company all say, look, Tianhe-2 is going to remain the #1 machine for the foreseeable future, for the next 3 or 4 years at least, until the other machines start to roll out. And so we still need to demonstrate how well can you carry out an application on the #1 machine in the world. People are looking at this, and so we need help in terms of more efficient deployment of like OpenMP-4 4.1. That's ready for prime time. We'd like to work in partnership with people that really know what they're doing in this area. This shows all of the other different devices. I'll let you look at this, but that's the main message. And these show, again, these are big hero sorts of runs for fixed problem size. And let me get to this issue, because we feel pretty confident that we're doing pretty well on the more conventional, well, not more conventional, but certainly on a homogeneous CPU system with the multi-threading. We've done very, very well with that. On the GPU-CPU hybrids like Titan, PSDANT, we performed pretty well. And but the challenge is with the Xeon Phis. So what have we done so far in our collaborative studies with Tianhe 2? We began by measuring the MPI bandwidth using the Intel MPI benchmark. This basically gives you a feeling for what the CPU to CPU host properties are, mic to mic, the native mode, CPU to mic, symmetric operation. And that gave us a feel for what was going on, but very quickly, so using the C version of our main code, we're able to operate in the symmetric mode very easily until we try to engage the Knight's Corner Xeon Phis. And then we ran into this issue with the offload mode version, which needs to be developed to address many mics on one compute node. Associated investigations include true weak scaling performance, as we talked about with increasing problem size. We'd love to do that on a huge system like Tianhe 2, starting from the smallest size up to the ITER size. We've done this successfully for the CPUs, up to over 8,000 nodes on Tianhe 2. But this is the big challenge, the deployment of 1 mic, 2 mic, and 3 mics respectively for these weak scaling performances. We're still working at it. Now, what about Stampede? That's the largest Intel Xeon Phi system in the US right now. This is, again, Knight's Corner. And we want to work on this because it's a natural lead-in for us to be able to then deploy on Tianhe 2, the #1 machine. And we have a good collaborative relationship with, this is the NSF's major center, and they're going to also upgrade to Stampede 2, which is a Knight's Landing system, very similar to Cori at Lawrence Berkeley Lab, and very similar to Theta. That's the machine that will lead to, I think within the next year or so, they're going to identify what the early science projects are for Aurora. But Theta is the machine that they're going to deploy first, but it's not a major step up yet, I mean, with respect to existing machines. As I said, so in the US, the comparable scale machines will be the Stampede 2 Knight's Landing system in Texas, the Cori system at Lawrence Livermore, which would be the first out the gate, and we'll probably hear more from Helen about that. And then the Theta device, which will be soon deployed at Argonne National Lab. So so in our interactions with the people at the NSF Center in Texas, we're trying to improve intra-node communications between the host and the mics to reduce the overhead and the MPI scatter operation. And this is, again, focusing on specific operations within our modern code. Improve inter-node communications between the mics for the particle shift operation, one of the 6 that I listed. Optimize particle loading for symmetric runs. Explore KNC Knight's Corner intrinsics. Initiate deployment of OpenMP 4.1 when that becomes available. This is a real urgent wish list item that we really want to move forward on. And it's really been nice being here to hear what people were talking about, the Intel experts, and it was very reassuring to hear them say, oh yeah, this is deployable now, you know, if you work at it. But what are the platforms you can try it out on? I was talking to Helen last night, and she says, well, you know, you have to have the platforms that can actually, that you can actually, once you modify your code to use OpenMP 4.1, there has to be some platforms that you can access earlier than later. And we'd love to do that. So more actively into the next phase, we need to move actively into the next phase of the true weak scaling performance studies with increasing problem size. Before we engage Tianhe-2, this big system. And you know, although Professor Liu, Yutong Liu, has been tremendously collaborative with us, and I had her on my author list of items here. She's one of the lead designers in China for both Tianhe-1A and Tianhe-2. And she's very interested these days in identifying more and more performance application codes. Because, by the way, there's an imperative from the leader of China, Xi Jinping, who got his degree in EE from Tsinghua. And so he's not a typical politician. He knows what he speaks in terms of technological advances. And he's made it clear to the leadership, HPC leadership in China, that we're very proud of you for producing the #1 supercomputer in the world, 2 different architectures within 4 years. But now we want to know, what good is this for the country? So the applications imperative is going to be very, very strong there. And they're driven to focus more attention on these things. So this speaks to what I mentioned, energy to solution estimates. If you do big production run codes, which we can do on different platforms, the natural question to then ask is, how much energy are you expending in going from one machine to another? And so we looked at, with the cooperation of the centers, this is Argonne, this is Oak Ridge, and this is the Swiss Supercomputing Center where Princeton, the #1 European machine, sits. We looked at performance on 4,100 nodes, CPU only, CPU plus GPU. And here's what to keep track of. How do you, the power expended per node, this is the time to solution here. This is on Mira, Titan, and Princeton. And if you run it CPU only, again, because of the communications through the Aries network, Princeton does very, very well relative to the others. The energy consumption also, Mira does very, very well compared to the others. But now if you go to the hybrid system, CPU plus GPU, for a real-world application here on a modern code, what happens? For the same number of nodes engaged, the power per node, as you see, goes up, very understandably, because you're engaging the GPUs now. The time to solution also improves. This is on Titan. It comes down to the best achieved on Princeton, but Princeton drops to about a little bit over 6 in time in these units. And the energy expended, if you look comparatively, this Titan, if you wanted to, like say, if you wanted to do comparative performance analysis between Mira and Titan, the 2 big US machines, this gives you better time to solution, but you also have expended significantly more energy. So, like right here. And but Princeton performs quite well. As you can see, this is comparable to what Mira was able to do in a CPU-only homogeneous system. So naturally, the Swiss Supercomputing Center is very happy with these results. This is not exhaustive. Very few applications are doing this right now, but because of the portability that we were able to achieve, and fortunately, with the access that we do have to these different top supercomputers, you can carry out this sort of thing. And the co-design people were very interested. In fact, we could not have begun to do these measurements of the energy consumption without the full cooperation of the centers and their engineers and such, because these power energy estimates were obtained from system instrumentation, including compute nodes, network, blades, AC to DC conversion, everything under the sun that I don't know in any kind of detail. But they worked with us for a concentrated period to help generate these results. And I think there's going to be more and more of this as we go forward and to explore the other platforms. We don't know yet. You notice prominently missing because we didn't achieve the performance that we wanted on the Xeon Phi Knights Corner systems. And so once that's done, Professor Liu at Tianhe-2 said, yeah, we absolutely can also come up with measurements of the energy dissolution on Tianhe-2. Now, why do I mention this? Because, as I said, the proper metrics to consider for applications is, in addition to performance portability, performance scaling, and so forth, is the metrics are time dissolution. How long did it take you to carry out a hero scale calculation? And then how much energy did it use? And then you do an economic balance between the two. How important is it to you that the application runs quickly? And then how much are you willing to spend in terms of energy to do it? And this is a interesting illustrative example in this direction. And whether you like it or not, it's the sort of thing that the large facilities are going to be dealing with going forward. So this is another thing that came up. Rick Stevens at Argonne National Lab said, well, how much work did you really have to put into making the codes portable? You know, what did you, how much time did you spend on these various things? So we came up with this little plot. This is for our most advanced simulations and such. This is CPU. This is if you add the GPU capability, and then this is for the Xeon Phi sort of thing. These are two different operations that I mentioned within our global PIC code. CPUs, of course, is the baseline lines of code. This means the change in the lines of code. This, you didn't have to change, so for a factor of almost 5 speed up with a GPU, you changed about a little bit over 700 lines. It's not a very complicated, cumbersome code like a lot of the CFD codes are. But to do the Xeon Phi thing, we're not very successful. What we've done so far, the speed up is actually a detriment right now. And so we need to improve that, and the change of the lines of code is about that. Now for this other operation, this is just one of 2 key operations in the PIC code. We do this comparative study of the lines of code that you have to modify just to give you a quantitative measure of some level of effort and such in doing all of this. To port and optimize our modern code to a specific architecture. And we're encouraged even though with things like this because when we first began working with the computer science experts in Kathy Ellick's group at Lawrence Berkeley Lab, people like Sam Williams and the other people in their team, the first version of, because we started out with a Fortran 90 version of GTC, and GTCP. And they worked with us to rewrite the code in C language. And and the first version of that was terrible. You know, if we compared that and actually ran that on real systems, the Fortran code was winning hands down. But then we stuck with it, continued to, in an interdisciplinary way, continue to collaborate with them, and then it just beat the pants off the Fortran 90 code because we were able to very efficiently deploy the multi-threading, the domain decomposition, and all these other properties that we're able to execute in a very timely way, you know, working with the more accessible language. You have to speak the language. The computer science people that we're interacting with, they're not going to stop and translate everything to Fortran for you. So that was very efficient. And so we're similarly encouraged that when you make your first attempts at these sorts of things, you're going to have your noses bloodied a little bit, and you just have to stick with it. And the fact that we've been doing well overall, big picture-wise, is quite encouraging. So, so we're looking at these operations, the push and the sort operations in the code. The speed up here measures for the GPUs, single node Kepler versus single Sandy Bridge node. For the Xeon Phi, single MIC versus 2 Sandy Bridge nodes. So, all right, this I should mention that you cannot sit still in being satisfied, although we're very happy with what our PIC algorithms are able to do right now. If you look going into the future, the schemes that we're using are still can be significantly improved in terms of the locality of the algorithms deployed. And one of the ways that if you turn to the applied math sort of area that we've also been in serious discussions with, you see what like other particle and cell codes applied to laser plasma interactions that was discussed by Kevin Bowers in about 2008. He used basically, although he didn't know he was using this, I've had a lot of discussions with him in recent years about the mathematical foundations that went into this VPIC code, which was a groundbreaking code that managed to run on the big machine, petaflop machine at Los Alamos, the Roadrunner, which is infamous for being very hard to program for. But Bowers did a terrific job on this, and he was a finalist for the Gordon Bell and had many articles and such published. But the basic applied math foundations or mathematics foundations is you can write down the Hamiltonian for the system, from which you can abstract the Lagrangian and then identify the action. These are all, mathematical physics descriptions. But then you can carry out a variational optimization of the system of equations. And then the challenge is to discretize it properly, and you obtain these symplectic orbits for the particle motion. What does symplectic mean? Symplectic just means to me that in common layman's language, that the more common sorts of time advances are like higher order, fourth order Runge-Kutta methods and such. Those are not energy conserving. So if you run them for a long, long period of time, you can look at the orbits and things. They eventually, lose their integrity after a while. Whereas symplectic orbits are like the Energizer bunny in the commercials, and it just keeps on going and going and going. So, so we've managed to look also at so this is the full all frequency sort of approach. The issues are it has limited applicability with respect to the size of the simulation region and also geometric complexity. That doesn't help us with the magnetic fusion problem with the toroidal donut-shaped-like geometry and everything. So we go back to the mathematical foundations of the geometric gyrokinetic formulation. And this is my colleague at Princeton. He also has a 6 months appointment in China. He's Dean of Research at the big Fusion Institute in Hefei. So this work provides the basic foundations for the symplectic integration of particle orbits and electromagnetic low-frequency plasma following the gyrokinetic ordering, which is what you still want to do. The still outstanding challenge is to address the reformulation of the non-local Poisson equations, because if you write down a Poisson equation, that's inherently global. It's not a local sort of representation. So how do you represent the field equations in a non-local way? And we're working on that right now. But it's just, I just put this up here because it says you have to always be thinking ahead. You always have to worry about your seed corn activities going into the future in these application domains, because to keep up with the architectural advances and things where you're going to need more, more locality in the way that you carry out the calculations. This seems like a promising approach and will be pursued. So these are my concluding comments. What I've tried to present to you is an illustration of a modern high-performance computing domain application code that's capable of scientific discovery while providing good performance scaling and portability on top supercomputing systems worldwide, together with illustrating the key metrics that I've emphasized throughout the talk: time to solution and associated energy to solution. OpenMP plays a key role in enabling scalable scientific software for extreme scale applications, with fusion energy science as an illustrative domain application. You don't have to be an expert in this area to appreciate this, but basically it illustrates here is an important domain application area that can engage computing at extreme scale. this is the most recent article that we have. Current progress is achieved includes deployment of innovative algorithms within a modern application code that delivers new scientific insights. As I showed, people weren't able to do this at scale on a very large problem size before. But this is carried out currently on all of these top supercomputers. Future targets include the 100 petaflop Summit project at Oak Ridge that we're already engaged in. We're also have access to Cori. Aurora is about to announce their recruitment of projects. I think we'll have a decent shot at getting into that. Stampede 2, the Knights landing system at the NSF Center there, we will have access to that. This is the big GPU system that's coming up in Japan under Satoshi Matsuoka's leadership at TaiTech, and we're working on a partnership with them too. So there's lots of evolving things here. It's very exciting, lots of interesting progress. Future progress will require algorithmic and solver advances enabled by applied math in an interdisciplinary co-design type environment together with computer science. We need better and better interactions. This has been discussed in detail here, the OpenMP-4.1, OpenACC, et cetera. We're working actively on moving forward to deploy these as soon as possible. And of course, tying this to extreme scale HPC domain applications such as ours, but also others. So I'll conclude with that. Thank you very much for your attention.
So your problems with scaling with Xeon Phi were because you only have symmetric mode code, so MPI on the code that works.
Right. We tried the offload mode, and the overhead was very difficult for us to deal with. We actually worked with people at the Texas Supercomputing Center, we didn't get as far as we needed to get. Actually, I have to say, you know, we're strongly encouraged to submit this for a Gordon Bell Prize entry this year because it's very different. Because most Gordon Bell Prize entries focus on performance on one platform, on one machine, and this is really spanning quite a few. But we came up a little short because we didn't succeed on the number one machine, the Xeon Phi system. So we're doubly motivated because you can always go back to the well, but we need to figure out a way to do this with respect to being able to efficiently deploy the offload mode. And our strategy going forward on that is to first work with your community here in figuring out how we can best deploy like OpenMP 4.1, which should help in a significant way. And then we have the platforms to try it out on. I mean, besides, you know, the advantage is we know the answers to a big, you know, hero-type calculation. And we've done this using other algorithmic approaches, run it on other computers, so we know how to hit the answer. Now you deploy, I don't know how hard, how long it takes. Let's say you try OpenMP 4.1, okay. You get it running, you have to first identify the platform we can try it on, and this maybe we can get your collaboration and access to get on a system earlier than later. That would be very exciting, because then we can see, you know, how far are you advancing on this? And then we can try it out on Stampede, which is going to be around for a while, the largest one in the US. And then once we've gained some confidence with that, then I can reapproach Professor Liu in China for Tianhe 2 and say, we're ready to, you know, not waste your time and such. We really are ready to try, you know, your full system. And so that's our strategy going forward. But where we're missing, you know, what we're missing, and this is, you know, full disclosure here, is that we haven't been very successful with the offload mode.
And that's also what you need in order to use more than one.
Yes, more exactly, because it's the communications between the host and then with Tang 2, there's 3 of these Xeon Phi processors, and that's a pain in the neck to figure out how to do that.
But you have the same issues with the GPU, and you get good success on GPUs. They don't call it offload mode, but they're still hitting that same bottleneck between CPU and
No, that's certainly true, Tim. But we had a lot more time to work on that with the algorithms people, and there you have to deal with the atomics and so forth, and the multi-threading issues are challenging there too. And there, that's a really good question to raise, because the other, we managed to do a CUDA version of this code, okay? And that's the best performance you're going to get, you know. But as we add more physics, you know, which is evolving, that's why we're so interested in OpenACC, because that's higher programming level, and you can do that, but then and you can test against what CUDA gives you for the problems that you're doing now. So we're also very interested in OpenACC and working on that too.
Okay, I can't resist.
Pardon?
I can't resist. Look, if you had used OpenCL instead of CUDA,
Uh-huh.
you'd be able to run. Well, no, wait a minute. There's 2 pieces to this. You'd be able to run on the Xeon Phis right now using the same code using the GPU. Now, wait a minute. I have just one more piece of this. If you're going to make the same mistake if you go OpenACC, you know, it's like you'll create a version of the code that will work very well on the wonderful NVIDIA platforms, but it won't work well on Xeon Phi. So don't make that mistake a second time. You made it once by locking yourself in with CUDA, by not going with an open standard. You're going to do that again with OpenACC? Don't you learn from your mistakes?
Well, you know,
Then the point of this, though, really was go with OpenMP 4.0. You got, you know, Intel people here who are close to the development team that can make sure that you're getting a technology that works. And don't spend time with OpenACC, because you'll lock in and you won't be able to try out the full diversity of platforms.
So what's missing from OpenMP 4.0
Yeah.
that you need in 4.1? What do you know what problems 4.1 will solve?
I don't know specifically. I just know that 4.1 is really what people are pointing to, is saying, you know, this is a significant improvement over 4.0. I think the experts here can probably speak more to it, but I don't want to venture into that and just say, you know, what specific pieces of our
I
code.
just challenge you to go back to your team and just point out that, you know, we locked ourselves in one, let's not do it again. So don't go that OpenACC route, go the OpenMP 4.0 route. Then you can go back and forth.
That's a reasonable comment, Tim. I'm totally agnostic about this because I look at this from an applications domain perspective and say, you know, whatever platforms work the best, and we want to be able to do this comparison, and whatever programming languages work the best, and so we're just, you know, keeping an open mind about these things. And for sure, I mean, you know, if it's very clear that, you know, when you show examples like, wow, you know, even for the present GPU, CPU systems, that the Aries network makes a big difference in our code. You know, that just hits you in the eye and just says, come on, you know, you're not going to keep on going down this trail with other things.
Okay, I apologize. I think we're running a little bit late, and I need to close the session. Thank you very much to Professor Tang.
If people want to follow up with other questions, I'm here for the rest of the day. I'd be delighted to talk to you all, especially experts from Intel and such. That'd be just great.